but it would allow us to keep burning fossil fuels. Now, here's another way we could continue to burn fossil fuels, which we seem to be good at doing. We know how to do. We have the technology for doing. We could burn the fossil fuels, but we could prevent the carbon dioxide from getting into the atmosphere. And this approach entails something called carbon capture and sequestration, CCS. And in these CCS schemes, one captures the carbon either before or after the fuel is burned, and one puts the carbon somewhere, typically deep underground, possibly deep in the ocean, and keeps it out of the atmosphere. How would these work? Well, first of all, I want to remind you that CCS is a daunting problem because unlike the pollutants, sulfur, mercury, other stuff particulates that we can remove from the exhaust streams of combustion processes in the tailpipes of our cars and the smokestacks of our power plants, carbon dioxide is what we want to produce when we're burning fossil fuels. So there's a vast amount of it being produced, as I mentioned before, from a typical large power plant, a 1 gigawatt power plant, a 1,000 megawatt power plant, typical of a medium to large size power plant these days. We produce about 1,000 tons of carbon dioxide every hour. We would have to capture that carbon dioxide and sequester it. First of all, we have to capture it from an even vaster gas stream because most of the atmosphere is nitrogen, and most of that nitrogen just goes right through the power plant and comes out the smokestack unaltered. A little bit of it combines in the high temperatures to make the nitrogen oxide pollutants. That's a problem too, but most of the nitrogen comes through, so we have this vast amount of gas coming out of the smokestacks. We have to remove the carbon dioxide, which is a vast amount itself, 1,000 tons an hour. Then we have to pump it deep underground and somehow keep it out of the atmosphere for very, very long times. That's a big technological challenge. People are working on that challenge. One way to make it a little less challenging is to process fuels before they're burned and try to remove the carbon then. Since these fuels contain hydrocarbons, you can then be left over with hydrogen, which you can burn as a fuel, but you've taken the carbon out beforehand, and that's an easier thing to do than remove it from the gas stream after combustion. On the other hand, you've removed some of the carbon, which contains some of the energy. If you combined it with oxygen to make CO2, you'd get more energy out, and you've lost that energy by taking the carbon out that way. Sequestering means you have to store the carbon where it simply can't escape. And where is that? Well, scientists believe that one place is in rocks that are saturated with a brine, a kind of saltwater solution, and you can pump the carbon down there, the carbon dioxide down there, and with the right geological formations, geologists believe it can stay trapped there for thousands of years without leakage. Now, obviously, if the carbon leaks back up and into the atmosphere, you haven't done anything, and you've wasted a lot of money and energy and other things to do that. But if you could find a geologic formation where it could be sequestered, that would help a lot. Another place to sequester it is in oil fields. The Earth is full of old oil wells, abandoned oil wells where we've pumped all the oil out. In fact, carbon dioxide is a commercial commodity for the oil industry. They buy it and they pump it down into oil wells where it helps bring up the last residues of oil down in the wells. So there's a kind of nice symbiosis there. If you produce carbon dioxide from fossil fuel combustion and you capture it and you pump it down abandoned oil wells, you may bring up more oil and get some more energy out. That's a possibility. On the other hand, regions full of oil fields may have uncharted oil wells that act as possible leaks for the carbon dioxide to get out from the atmosphere into the atmosphere. So that may not be such a good idea. There are also those who advocate putting carbon dioxide deep into the bottom of the ocean, where under this enormous pressure it would presumably stay. That would solve several problems. It would get it out of the atmosphere. It would keep it out of the surface waters where it's causing acidification problems, as I pointed out. But we don't know enough about the ecology of the deep ocean or the movement of the carbon dioxide in the deep ocean to be sure that that method would work. There are some trial plants that are doing that off the coast of Norway and some other places. There's a trial operation in Canada taking carbon dioxide from power plants in the Dakotas, but these are just small pilot projects going on right now. And I should mention, CCS is obviously a technologically difficult thing to do. It's obviously an economically expensive thing to do, and it also consumes a huge amount of energy. To pressurize carbon dioxide and pump it deep into the ground or deep under the ocean takes a lot of energy. So a CCS-equipped power plant may require something like 40% more fuel, 40% more coal, 40% more natural gas, whatever, to produce a given amount of electrical energy, say, than it would if it didn't have the carbon capture and sequestration technology. But CCS is something that people are looking actively at, and I must say, after a report on this by the IPCC, I used to be a skeptic about this. I thought it was just a way of keeping the fossil industry going. Now I think it's something we ought to look at as one possible step of many in the solution to the problem. But I don't have high hopes for CCS. And I think we need to wean ourselves from fossil fuels for a number of other reasons, including their pollution effects and their scarcity. So I don't think CCS is a long-term solution, but it might be a short-term solution till some of those longer ones can come online. A third possibility is that we could switch from the fossil fuels to the various energy alternatives that I described in the previous lecture. And I want to be realistic here. Of those, only nuclear fission and hydroelectric power are currently developed at the large scales that we need to supply a significant fraction of the world's energy. And both are at present suited only to one thing, namely electric power generation. So of all the things we do with energy, electricity, by the way, is one of the most versatile forms of energy. Nuclear fission and hydropower basically are good for producing electricity and not much else. The hydro resource is almost fully exploited in the industrialized countries. You can talk about building small-scale hydro in your state in the United States, and maybe there are places you can do it, but I guarantee you, you aren't going to get a great deal more power out of hydroelectricity because almost all the hydro sources are developed. In fact, in some states, we're taking down old hydro dams because they have ecological consequences we don't like. The nuclear option is a different story. This is not a course in nuclear power. I could go into the whole thing, but you know there are some problems with nuclear power. I would argue that those problems may not be as serious, with the exception of proliferation, as many people think, but still there are questions to be raised about nuclear power. There are other alternatives. In particular, there are the direct and indirect solar technologies that I discussed. The conversion of sunlight into electricity through photovoltaics, the conversion of sunlight directly into heat through simple thermal solar collectors, the use of solar concentrators to make heat engines, basically thermal power plants that run on sunlight. These are all possibilities. The use of indirect solar energy, wind power, also growing very rapidly at about 30% a year, especially in Europe. Denmark gets about 20% of its electricity from the wind, for example. These are coming along. They have considerable promise. They are advancing technologically very rapidly. Wind power in some areas is becoming competitive with ordinary fossil fuel-based grid electric power. And I think that's a good thing. But a single wind turbine of the largest size produced today makes perhaps 5 megawatts of electricity at its peak. A single large coal-burning power plant produces 1,000 megawatts, 200 times as much. So you need a lot of wind turbines to replace coal-fired power plants, and the coal-fired power plants run round the clock, and the wind doesn't necessarily blow round the clock. So you've got to be realistic about these things. Nevertheless, the direct and indirect flows of solar energy, direct use for photovoltaics and so forth, indirect use of wind, water, and biomass do have serious potential for replacing fossil fuels. But the most promising of those, at least in the long term, like photovoltaics, are simply not developed technologically or economically to the point where we can switch them in. Now, having said that, this is as close as I'm going to get to policy in the whole course. We have been subsidizing the fossil fuel industry in many ways for a long time. For instance, we subsidize highways as a means of transportation in the United States over, say, rail, which is also fossil-powered, although if it's electric, it could be nuclear-powered. We give oil companies depletion allowances as they remove oil from the ground. There are many things we do that encourage the use of fossil fuels through policy. One of the discussions that's been going around in the IPCC circles and environmental circles in general is the idea of a carbon tax. Tax fuels on the basis of how much carbon they put into the atmosphere. We could do that, and that would be a policy change. And a policy change like that would change the economics of where, say, photovoltaics sit relative to coal power. It wouldn't be enough at the present to reverse that economics, but it would help. And my point is there are policy decisions we could make that would take the economic ordering of these technologies and change it a little bit in favor of the non-carbon technologies. And you may or may not want to do that politically, and that's not what this course is about, but there are ways to nudge things in more favor of these non-carbon technologies. And it isn't as though right now it's a level playing field. It's quite different from that if you look at the subsidies, direct or indirect, that we have for carbon-based fossil energy. Now, I could imagine a distant future in which we have carbon-free energy that's coming from, say, solar photovoltaics or from nuclear fusion, and that produces our electricity, and we take that electricity and we use it to split, as I said before, water into hydrogen and oxygen, and we use that hydrogen as a fuel for our portable transportation vehicles. That's a completely carbon-free energy future. And it could be fusion powered or it could be solar powered. And I think we could have that in 50 years. But we need to do something well before 50 years to get our carbon emissions under control. So that's a goal to have for the distant future, but to be realistic, that's not where we're going to be now.